In this video, we're going to continue finding area of regions between curves, but we're going to look at it from a different perspective because sometimes it makes more sense to draw rectangles in a different direction. So I have a picture here for you of a region that we need to calculate the area of. And if we were to do this using the same methods as yesterday, we would actually have to split this shape into pieces and calculate the area of both the left and then the right and add them together. And the reason is because when we calculate the heights of those rectangles, I have to use the blue function on the left, but on the right, I'm using the red function. So I would have to set up two completely different integrals. It's not the end of the world, but sometimes it's more convenient to just set up one. Also, eventually, we're going to take this region and we're going to revolve it around the y-axis. And in that case, we have to change our perspective. And so rather than drawing vertical rectangles, we're actually going to draw horizontal rectangles. And so we're doing the same idea. It's just that I'm going to calculate the width of this guy. So, the area of the rectangle. So I need length times width. Well, in this case, my length is going to be the distance between the red and the blue. And then the width is going to be some very, very small change in these y values. So in this case, we're going to respect y instead of x. And it just allows us to set this up in one function. The key to remember here is that on the x-axis, larger values are on the right and smaller values are on the left. So when I'm calculating this horizontal distance, I'm always going to take the function on the right because it's larger minus the function on the left because it's smaller. Also, when we're respecting y, our bounds must be y values. So again, we put the smaller bounds on the bottom and the larger bounds on the top. So whatever your first y value is, and then your final bound would be wherever your last y value is. So here's an example, and there's like probably I would say three really good ways to graph these equations. First of all, one way that I like to do this is I like to just change my perspective. So if, let's say, we looked at this in a normal equation, usually this is y, usually we would have 3 minus x squared. If I were to graph that, that would be a parabola. It would open downward, and it would have a y-intercept of 3. And this is what it would look like. Because we're now respecting y instead of x, all we need to do is change the perspective that we're reading this graph. And so instead of it opening downward, it actually opens here to the left. And so this process, you honestly can even just tilt your head. And when you tilt your head, you're actually looking at this as now the top of your graph. This is the bottom. You're looking at this as the right, and this as the left. Just remember, on the y-axis, values up top are positive and values below are negative. So when you tilt your head, your graph ends up kind of looking backwards. And we'll talk about that more in class. That causes this guy to kind of look a little bit backwards if you're graphing it to change your perspective. But this will be linear, has a slope of +1. Because our perspective is backwards, if you tilt your head, it's not going to appear as if it's increasing. It's actually going to appear as if it is decreasing, but its y-intercept is 1, so it has to go through that point, and it's going to look something like that. Okay. Another way to graph this, which may in some cases be easier, sometimes maybe not, is to just make a table. And so normally when we make a table, we choose values of x. Well, in this case, y is inside the function, so we're actually going to choose values of y. So if I choose, let's say, -1, I'm going to get 3 minus 1. If I choose 0, I'm going to get 3. If I choose 1, I'm still going to get 2. And then when you plot those ordered pairs, we see that 2, -1 is going to be right here. 3, 0 is here, and 2, +1 is here. And we could, again, even come up with more ordered pairs in order to find what the graph would look like. Finally, if you wanted to, you could get y by itself. You will get two equations. The first equation will be the positive square root, and the next equation will be the negative square root. So there's lots and lots of ways to find out what these graphs look like. In class, I'll kind of show you. You can just tilt your head But for now, it's probably easiest to understand that we can always just make a table. And so here, again, if I choose like -1, 0, and 1, when I plug in -1, I get x equals 0. When I plug in 0, I get x equals 1. And then finally here, I'll get x equals 2. If I were to actually graph these, 0, -1 would be here, 1, 0, and 2, 1. So you can see my line didn't quite go where it needed to, but you get the idea. Okay? So what we're going to be doing is we're going to calculate the area of this kind of enclosed region right here. And it's going to be easier to draw horizontal rectangles versus vertical rectangles. And again, the reason is I would have to split this shape up right here in the middle because these rectangles have heights that are going to be the red function minus the blue. Over here, my heights are going to be the black function minus the black or the blue. And so they're just calculated in different ways, so we would have to set up two integrals. If I respect y, I can draw rectangles in a horizontal manner, and I'm going to take the quadratic minus the linear. Even when I'm down here, I can calculate quadratic minus linear. So that's going to allow me to set up only one integral and calculate the area faster. Okay? So, just like before, I need the distance of this green line, or basically the height of this very thin rectangle. And I'm going to use my quadratic function minus my linear. So I'll have the quadratic function minus the linear. And this is going to give me the length or the height of each of those rectangles. And then their very small width is going to be dy. So this is like length times width. That calculates the area of each rectangle. My integral is going to add them all together. I just need to make sure now, since I'm respecting y, that my bounds are y values. So my first rectangle occurs way down here at this point where they cross. And my last rectangle is going to be up top at the point where they cross. And since there was no point of intersection given, I do need to find that by setting my equations equal to one another. So 3 minus y squared equals y plus 1 will give me their points of intersection. And you should hopefully see that we actually already know this one just because we made those tables. But if I take everything to one side, I'm going to get 0 equals y squared plus y minus 2. If I factor, I'll see that I get y plus 2, y minus 1. And that means our solutions are -2 and +1. And actually my picture's not quite right, but anyway, they cross at y equals -2, and they cross at y equals +1. Okay, so those are going to be my bounds. And if we were to calculate the value of this, that would give us the area in between the two curves.